Introduction. In this lecture, we'll delve into the optimization of a multivariable function, a fundamental concept in mathematical economics. We'll employ the method of Lagrange multipliers to find the optimal values of variables that maximize or minimize a given objective function. Problem statement. Consider the following objective function. Z equals 4x caret 2 to 7x 2xy 5y plus 4y squared. Our goal is to determine the values of x and y that either maximize or minimize the value of z. First order conditions, FOCs. To find the critical points, we take the partial derivatives of z with respect to x and y and set them equal to 0. Partial differential z, partial differential x equals 8x 7 to y equals 0. Partial differential z, partial differential y equals minus 2x5 plus 8y equals 0. Solving these equations simultaneously will give us the potential optimal points. Second order conditions, SOCs. To classify the critical points, we use the Hessian matrix. H equals squared z, partial differential x squared z, partial differential x, partial differential y, squared z, partial differential y, partial differential x squared z, partial differential y squared. Calculating the second order partial derivatives. Squared z, partial differential x squared equals 8. Squared z, partial differential y squared equals 8. Squared z, partial differential x, partial differential y equals squared z, partial differential y, partial differential x equals minus 2. The Hessian matrix becomes H equals 8 minus 2, 2, 8. To determine the nature of the critical point, we evaluate the determinant of the Hessian matrix. Det H equals 6 or greater than 0. Since the determinant is positive and squared z, partial differential x squared greater than 0, the critical point corresponds to a local minimum. Economic interpretation. The specific interpretation of this result depends on the context of the problem. For instance, cost minimization. If z represents a cost function, the optimal values of x and y would indicate the input levels that minimize the total cost. Profit maximization. If z represents a profit function, the optimal values would maximize the profit. Conclusion. By applying the method of Lagrange multipliers and analyzing the second order conditions, we've successfully identified the optimal values of x and y that minimize the objective function z.